Hi, this is Dr. Emenacker. In this particular video, we are going to continue working with limits, and we're going to look at evaluating the continuity of a function at a given point using limits. The idea of continuity is very important in calculus. In fact, you can't do derivatives without it, which would shoot down half a calculus right there, derivatives. And you can't always integrate under a function that isn't continuous, which would take out the other half of calculus. So continuity is an important concept to look at. We're going to do this in three steps. First, just going to talk about the concept of continuity in general. Um, it's fairly easy to describe. However, establishing it mathematically gets a little bit trickier. And then we're going to practice testing for continuity using several different functions at a given point. Okay, so first off, what is the basic concept of continuity? Basically, the idea is, can you draw the graph without lifting your pencil? That's it. Of course, if that was all there was to it, the video would be a short one. What we're going to need to do is look at how do you prove mathematically that something is continuous or not continuous. Now, let's take a look at a variety of different functions here and or graphs. You can have corners on them like this. It's actually called a cusp, okay? And that's fine. That is continuous. You can have situations like this. You've seen this type of situation where this is a cubic polynomial. That's fine. I was able to draw it all in one sweep without lifting the pen or the stylus. However, here comes the other part. There are situations where, for example, you might hit a vertical asymptote and a horizontal asymptote, and maybe the graph goes like this. And then the other portion of the graph goes like this. This is an example of something that is not continuous at a specific point. That point being x equal to some number I'll call a. Okay, the function of this would be something like 1. Doesn't have to be 1, could be 2, 3, 4, whatever, over x minus a. Whatever this number for x is, this could be 1 or 2 or 5. That same number winds up down here in the denominator. It's broken apart there, or this is called a point of discontinuity, because if we put in the x value, whatever it might be, for example, 1, in the denominator, we'd have 1 minus 1 is 0, which would give us a fraction with a 0 in the denominator, and that's not a good thing. It's undefined. Okay, so we have one location, one point of discontinuity. With that said, on either side of this vertical asymptote, this function all the way along over here, as well as on the right-hand side, all the way along over there, is continuous. Because as you saw when I drew the function, I was able to, with one sweep of the stylus, create the left-hand portion, and then with one sweep of the stylus, create the right-hand portion. So this is an example of a graph that has a point of discontinuity. Let's take a look at another scenario. You can have a graph that goes like this, and then picks up here and does something or other else. And I'm just going to make up some x value. We'll say that's 2. To the left of 2, the function is continuous. I was able to draw that line without picking up my pen. Starting at 2 and moving to the right, that's continuous. Because once again, I was able to or draw it without picking up my pen. At the location x equals 2, we have a point of discontinuity. Okay, so there is a point here, an x value, where this function is discontinuous. If we're only working on the negative side, negative x values, the function's fine. It's continuous everywhere on the negative side. If we're only working with values of x that are bigger than 2, once again, we're in great shape because to the right of 2, everything's great. It's continuous. But at 2, it's not continuous. You can also come up with situations like this. And I'll just change up the number and say this is x equals 3. Now, at x equals 3, this function has a discontinuity. Okay, you cannot draw that function as it exists without lifting up your pen or pencil or whatever it is. Okay, as with the previous one, if you're to the left of 3 or to the right of 3, the function's fine, it's continuous. Okay. Now, there are other functions that we're going to encounter. An example of this type of function in real life, these are called stepwise functions. An example would be, for example, the shipping charges. If it has some minimum weight up to a first weight, let's say 1 pound, it ships for, let's say, $3. If it's slightly heavier than 1 pound, up to 2 pounds, it ships for, I'm just making this up, $5. If it's slightly heavier than 2 pounds, up to 3 pounds, you get the idea, another shipping cost. Okay. Stepwise function, called this because it looks like a series of steps. On any one set of x values, okay, for example, this set of x values here, not cooperating. This set of x values here, okay, it's continuous. But then there is a point of discontinuity at 1. Moving further along, you'll see there's a point of discontinuity at 2. The same thing at 3, and all along the way. So there are functions that we can come up with that are continuous everywhere. The first 2 examples were continuous everywhere. The last 4 examples are piecewise continuous. That means that pieces of them are continuous, but over the entire domain from negative infinity to infinity, yeah, it's not going to work. All right, so we've got a basic idea of what continuity looks like. We need to have a mathematical way to test for continuity. So let's take a look at a mathematical definition. This definition has 3 pieces to it. Each of the 3 pieces is necessary, but no one of these pieces by itself is sufficient to say that the function is continuous at a particular point. It's kind of like saying, well, gosh, give me a kind of a general description of what dogs look like. And if you say, well, they have 4 legs, well, that is a necessary part to get a general definition of a dog, but it's not sufficient. You walk up to a giraffe and say 4 legs must be a dog. Okay, so all 3 parts have to come into play before you can actually say that the thing is continuous. The first element is if you evaluate the function at a specific point that you're looking at, it exists. Okay, so what we're looking at here is a mathematical definition of continuity at a point. And let's say that that point is x equals a. So the first thing is you have to be able to take that value for x and plug it into the function, and the function's fine. It exists. The second thing is that the limit of the function as x approaches a also exists. Now, what the first requirement does is it says when you get there, that location has to exist. The second component in this definition, the limit, is talking about as you get closer and closer, it looks like we're headed to the same point that we're talking about in the first of these 3 criteria. The third one, and this is important as well. The third criteria is that the limit of the function as x approaches a must equal the actual value there. So what this is saying is where it looks like you're heading is where you actually wind up. The limit talks about where does it look like we're going. F of A talks about where do we really end up once we get there. Let's take a look at verifying continuity of several different functions. Just practice it. In each and every one of these cases, we're going to have to go through all three steps. If any one of these steps fails, the function is not continuous at that location, x equals a. It could be continuous elsewhere, just not continuous there. So let's take a look at example 1. In this example, let's verify that f of x equals 2x plus 3 is continuous at, let's say, x equal to 4. Well, first off, before we even get started on this, let's think about what we're working with. This particular function is a line. So we know before we even get started, this thing is continuous anywhere. So it should come as no surprise when we finish this off that it's actually continuous. But let's use this as a first example to go through the 3 steps in the process of verifying that a function is continuous or proving that a function is not continuous. Step 1, does the function exist at the point of interest? So step 1 says we're going to evaluate the function at 4. 4 being the point of interest. X equals 4 is our point of interest. Okay, so we're going to evaluate the function, and this is going to give us 2 times 4 plus 3 equals 11. Okay, so we've got that. Step 1 is fine. The function actually exists at that location. We need to now move on to step 2, which is to demonstrate that the limit exists at that same location. So the second thing is we need to verify that the limit of 2x plus 3 as x approaches 4 exists. Notice I'm not talking about what it's equal to or anything like that right now. I want to prove that the limit exists. For the limit to exist, this is important, be sure you catch this. For the limit to exist, this means that if we do this limit as x approaches 4 from the left-hand side of f of x, it must equal the limit as x approaches 4 from the right-hand side of this same function. This is what we're after right there. This means we're going to have to work on 2 separate limits. We're going to have to work on the left-hand limit and then come back and work on the right-hand limit, determine what the value is for each of these, and then look at those separate values and determine if they're equal or not equal. If they're not equal, the limit doesn't exist and we're done. So first off, let's go ahead and let's evaluate the left-hand limit. Okay, so this is going to be the limit of f of x as x approaches 4 from the negative side. Okay, so this is going to be the limit of 2x plus 3 as x approaches 4 from the negative side. In this case, we have a polynomial. Okay, we don't have issues with 0 in the denominator or anything like that. So what we can do, if you want, is we can set up a table. listing our x values and our function. Now remember, we're approaching 4 from the left-hand side, so that's going to give us values like 3.9, 3.99, 3.999. And as we get each of these values, what we're going to notice is these values are approaching 11. You can try this on your calculator. In fact, when it comes time to do the quiz, you're going to have to do this on your calculator and then copy it down. I'm just writing it like this to save a little time. Okay, so what winds up happening here is the left-hand limit equals 11. The next thing we need to do is we need to look at this exact same limit, except we're going to approach 4 from the right-hand side, and we're going to continue to use our same function. So if we set up a table, as we just did, we're going to have our x, we're going to have our 2x plus 3. And now, remember, we're approaching 4 from the right-hand side, so that's going to be things like 4.1, 4.01, 4.001. And you'll notice that as the calculator returns values for these, as you enter values of x that are closer to 4, the output is approaching 4 as well. So when we evaluate this function from the left and from the right, it's approaching the same value. These two, this result, along with this result, allow us to say, yes, the left and the right limits are equal. They exist and they are equal. Okay, so we can now do is we can say, yes, the limit as x approaches 4 of 2x plus 3 exists. All right, so we have addressed the first two concerns in verifying continuity. The third concern is that of the function equaling the limit at the point of interest. Well, as we've proved in the two steps above, the function is 11 and the limit is 11. So we have all three requirements listed and verified to demonstrate that this function truly is continuous at x equals 4. You need to go through all three steps on a quiz, test, or wherever if you're testing for continuity. All three of these must be the case. You can't just say, well, if it has 4 legs, it's a dog. Okay? If one of these three or two of the three work and the other one doesn't, you don't have a continuous function. Let's take a look at a second example. I'm going to use a different type of function this time. I'm going to use something like g of x is equal to 5x plus 1 when x is less than 2, and a negative 3x minus 2 when x is greater than or equal to 2. And the objective here is to determine if it is continuous at x equal 2. So is g of x continuous at x equals 2? It could be continuous elsewhere and not at x equals 2. All we're concerned about in this particular case right now is what's happening at 2. We're not concerned about what's happening at negative 3 or positive 7 or anything like that. Okay, so the first thing we're going to do, we're going to go through our 3 steps. We're going to evaluate g at 2. Well, to evaluate g at 2, we first need to determine, are we going to use the first or the second equation? If we're at 2, that's going to be where x is greater than or equal to 2, which indicates that we need to use the equation -3 times 2 minus 2, which looks like a -8. Okay, so that works. That's great. It exists. Okay. The second thing that we need to do is we need to determine, does the limit of g of x as x approaches 2 exist? Well, to do that, recall, as we did in the prior problem, there are two parts to this. Okay. Essentially, the whole screen there is verifying the second step right now. We want to do the limit from the left, then do the limit from the right. So let's come back down here. And the first thing we're going to do is we're going to evaluate the limit of g of x as x approaches 2 from the negative side. Now let's go back up to our function. It's at the top of the screen. If we're approaching 2 from the negative side, think of this again on a number line. Here's 2. If we're to the left of 2, we're going to be at things like 1, 0, -1. These values are all going to be less than 2, which is going to indicate that according to the function, we need to use this 5x plus 1. So when we evaluate this, we're going to do 5 times 2 plus 1 equals 11. So now we have a value for the function from the left-hand side. The next thing we're going to do is we're going to evaluate this exact same function, g of x, as x approaches 2, but this time it's going to be from the right-hand side. Once again, referencing the number line, to the right are things like 3 and 4, stuff over here. So our x values are now going to be greater than 2. Greater than 2, according to this function, means that we're going to need to use the -3x minus 2. So I'm going to copy that down. I'm going to do the -3 times the x value I'm interested in, 2, minus 2 is going to be -6 minus 2 is a -8. Now, notice at this point, we have the limit from the left approaches 11. The limit from the right approaches -8. What this is telling me is, as I draw the graph from the left, I'm going up to something or other where the y value equals 11. And as I'm drawing it from the right-hand side, I'm coming up to a function where the y value equals a -8. Clearly, with this gap, it's not continuous. Okay, so when you run into scenarios where the left and the right-hand limits are not equal, okay, this tells you that the limit as x approaches 2 of g of x does not exist. As soon as you get to that, you can stop. If it is not a situation where the limit exists at the point we're testing, you're done. Because as I drew in the lower right-hand corner, you can see it's headed in two different directions. If it's headed in two different directions, it can't be continuous. At this point, you can stop here and put down something to the effect of the function does not satisfy the requirement of the limit existing. The limit as x approaches 2 of g of x existing. Period. This implies, or this indicates, x equals 2 is a point of discontinuity. And you're done. Notice here I've explained why and not just said, nope, it doesn't exist and walk off. Okay, you need to provide some explanation on how did you come to the conclusion that it doesn't exist and not just say, well, gosh, but it's not there. Okay, so you need to provide some support. Okay, let's take a look at another one. We'll do one more. Let's say we have some function at h of x is equal to, let's see here, 2x plus 4 for x less than or equal to 1. And let's say it's equal to 6x for x greater than 1. Determine if this piecewise function is continuous at x equals 1. So the question is this continuous at x equals 1? I would encourage you to put your video on pause and work through this. Remember, you have to do all 3 steps. And from that, use the results to support a conclusion of continuity or a point of discontinuity at x equals 1. So go ahead and pause your calculator or your computer and give this a shot. All right, so hopefully you actually did pause your computer and try this. There are 3 steps we need to do. First, we need to evaluate h at 1. Well, h equal to 1 is going to put us into this. Okay, so this is going to give us 2 times 1 plus 4 equals 6. Okay, so it exists. That is fine. All we need to know at this point is that it exists. Second thing, we need to evaluate the limit as x approaches 1 of h of x. Recall, to demonstrate that the limit exists, we need to deal with the left-hand limit. So we need the limit as x approaches 1 from the left-hand side of h of x. In addition to checking the limit from the left-hand side, we're then also going to need to evaluate the limit as x approaches 1 from the right-hand side of this same function. Okay, now you can do this either using the calculator as we did in the previous one, or you can also say, in both cases, x less than or equal to 1 or x greater than 1, what we have here are lines, and those things are continuous. So we can just go ahead and evaluate. If we're coming in from the left-hand side, we have the first function. And we evaluate that, and we get 6. So coming in from the left side, I use this because that's for x less than 1, and we get a value of 6. Then coming in from the right-hand side, which is x greater than 1, I'm going to use this, which is going to allow us to then say, okay, we have 6 times the 1, which is 6. Now notice here that the left and the right-hand limits are equal. If the left and the right-hand limits are equal, that tells us that our limit over here to the left exists and it has a value of 6. Okay, so there's step 2. Now, the third step in the process is to determine, does the function h at 1 equal the limit as x approaches 1 of h of x. So this is the third step. As we determined in step 1, this has a value of 6. Then, as we determined with the limit that we just did, it approaches 6. So what this says is when you actually get to x equals 1, you're going to be at a y value of 6. Then the right-hand side with the limit says whether you're coming in from the left or the right-hand side, it looks like we're headed to 6. So it all boils down to it looks like we're headed to 6, and when we actually get there, sure enough, we're at 6. So this function is continuous at x equals 6. Now it's very important to put down the location where you have your point of continuity. I'm sorry, at x equals 1. At x equals 1. The x that we're concerned about is 1. Okay? It's very important that you put down a location because it may be continuous in one location, but not continuous in another location. I would encourage you to practice this a number of times. Be sure that you go through each of these 3 steps. Just take them one at a time. And it is entirely possible for the first 2 steps to work. For example, it is entirely possible at step 1, and I'm just making up something here, for k of 7 to equal 8. At step 2, you do the limit as x approaches 7 of k of x. And when you do the limit, it does exist, but it equals -4. That's possible. Both of these exist. Things are fine as far as them existing, but it fails at the third step. K at 7 and the limit of the function as x approaches 7 are not equal. So it's possible for step 1 to fail. It's possible for step 2 to fail. It's possible for steps 1 and 2 to both work great, but then when you get to step 3, they aren't equal. If any of those situations happen, it's discontinuous at that specific x value. Okay, so hopefully this will give you some ideas on how to prove or test for continuity of a function at a point.